Okay, so let's look at the questions from the tutorial 5, the complex number. Okay, so this one, okay, it's use the De Mor's theorem to show that we have got the cos 6 theta is given by this expression. Okay, so we have to we start with the De Mor's theorem. Okay, so the De Mor's theorem tells us that the cos 6 theta plus I sin 6 theta is actually like we have got the cos theta plus I sin theta to the power of 6. And from here, what we got to do is, okay, we really have to expand it, okay, by using the binomial expansion. Okay, so as we actually deal with the binomial expansion here, right, we will actually have got like different parts here. So some of the terms will give us like a real part, and some of the terms will give us the imaginary. Okay, so just collect the real and the imaginary together. And after that is, okay, we look at okay, here we want the cos. So the cos is the real part. So we're just taking the real part from that. Okay, this is a real part. But still, okay, in our real part here, right, we have got a lot of the sine square, sine power 4, and sine power 6 still. So those like sine square, we need to replace it by the 1 minus cos square. Okay, so this is like sine power 4, which is like a 1 minus cos squared squared. Sine power 6 is actually 1 minus cos square. We have to take the cube of it. So after that, it's not much, okay, that we got to do. We just have to like expand everything, cancel off, and tidy up. Okay, so we're actually able to show that already. So with the result there, right, okay, it says hence of this equation, giving each root in the form which is like a cos of a k pi. So from what we actually see from there, right, okay, usually the identity is related to the equation there. Okay, it's somehow related by, you can see like the coefficient there are sort of like double. Okay, but the difference is just okay, why is it like we don't have like a negative one here? So the thing is, okay, we just need to make, okay, the cos 6 theta equals to a certain value. Okay, so we can actually try to rearrange, okay, the equation a little bit. Okay, so from what we actually do is, okay, we let all these to be the x, okay, the cos theta to be the x there. So you can see this is what we did in the first line here. And we are just trying to like make the right-hand side into the equation. Okay, so we try to make the right-hand side there into the equation. And from there, we're able to identify already. So we are actually getting the equation there, right? When we actually let the cos 6 theta is equal to negative half. So from there, we need to solve, okay? Cos 6 theta means we need to write out the values for the 6 cycles for like the, when we solve for the negative half there. So these are all the values that we get, okay, for the theta there. Okay, so because here we are trying to solve for this equation here, which is power 6. So it means that we will actually have got 6 roots, and all the roots there, they already mentioned that, okay, it is actually in the form of like a cos of the k pi. So from there, we just need to give like distinct values of the cos k pi then. Okay, so for this set of the values here, right, for the k, right, it's not unique. So not necessarily that you need to must have like these 6 values here. You could, okay, give any other values of k, all right, as long as your cos k pi, they are all different values. Okay, because we know that the value of the cos k pi, right, they are actually like in like the first and the last has the same value, the second and the second last has the same value for the cos, and so on. You just need to give the 6 values here, which are like distinct. Okay, so like I said, you don't necessarily have to give the value which is like this set. Any other set of the value will be accepted. Okay, so again, as long as they are distinct, or we say they are not repeated. Okay, right. So the next question here is, okay, to find the roots of this equation. So z cube is a minus 4z3 plus a 4i. Give your answer in the form of REI data. Okay, so how can we actually do that is we can actually use a bit of the formula there. So first, okay, is to actually write that number that we see at the right-hand side there, right? The minus 4z3 plus a 4i, okay, as the polar form or the exponential form, okay? But as long as we find what is the modulus and the argument of it, okay? So with that, right, we can actually take like the cube root for the modulus there, okay, for the original number. And then remember the formula that we have here, right? It's alpha over n plus a 2p pi over n for the argument. So the argument here is like this is the alpha over n plus the 2p pi over n there. So after that, okay, the p value, okay, usually it's just we sub in the 0, 1, and 2 there. Okay, so we sub in the 0, 1, and 2 there. So all the three roots is actually given as this. Okay, so those are the three roots there. So denoting these roots by Z1, Z2, and Z3, and show that for every positive integer k, when we actually power 3k each of the roots there and we add them together, it is giving us this result here. Okay, so let's see. So for each of the root that we actually power 3 already. So power 3k, sorry. So when we power 3k, we get this is like 3k, right? And then this have to multiply by the 3k as well. So we do the same thing for all the rest of the roots there. So we realize that, okay, the 2 power 3k can be factorized. And all these angles, right, like 17k pi over 6 is actually like something that is more than 2 pi already. Okay, which it can be actually reduced to like 5 over 6k pi I. And also same thing to this one here. This is actually something that is over the 2 pi already. So we just keep on minus the 2 pi until we get the angle here, which is within the 0 to 2 pi. So they're actually like having the same value for each of the term there. So basically after that, it's just giving us like the 3 times this thing, okay, the 2 power 3k, e power 5 over 6 k pi I like that, right? So this is the next one here. So write down all the 8 root of the unity. Okay. So for this first part of the question, right? When we write down the 8 roots of the unity, of course, it's actually like 2p pi over n. Okay, for the argument, this is for the unity, yeah. So the roots here is like having like the argument, which is like 2p pi over n. Okay, so 2p pi over n here gives us like p pi over 4. So we could, okay, I mean the value of the p here, right? We could choose to write from 0 to 7. Okay, we can write from 0 to 7. Okay, it's also accepted, not a problem. But for myself, right, I'm actually going to like move the 5, 6, 7, okay, to become the negative values there. So that's why we get like -1, -2, and -3. So this is why you can see the value of the p that I'm trying to write here is like 0, plus minus 1, plus minus 2, plus minus 3, and also a 4 then. There's no right or wrong for this part of the question, okay? But why do I actually write in these like plus and minuses is because we are actually going to use it in the later part where, okay, in the second part here is to do the verification a little bit. So we can see like when we actually expand, right, the coefficient of the z here gives us something like this, okay, which is something that we love, okay, it's 2 cos theta, okay, this is an identity that we could actually use, okay. So with this, right, okay, and then they actually ask us to express the z power 8 minus 1 as the product of the 2 linear factors and 3 quadratic factors, and the coefficients are all real and also like this in non-trivial form. So what happens is that because, okay, the z power 8 minus 1, right, when we actually want to write that into the factors, okay, so how do we actually write the factors here is that we have their roots, okay, we need each of the roots there. So for each of the roots there, right, it can be actually obtained from the first part here, okay. So from the first part here, the roots that we actually have here is, okay, this is for the p equals to 0, we get e power 0, p equals to 4, we get this, and so on. This is p is equals to 1, p is equals to -1, p is equals to 2, -2, 3, and -3. Okay, so once you actually have like all these like linear factors, okay, written in their roots there already, right? So you can see the good thing about like we are using the p where we have got like the plus, minus 1, 2, and 3 there, right? Is we can actually use the result from the second part. We have already sort of like proven that in the second part because the second part here talks about like the theta and the negative theta of that. Okay, so from the second part there, okay, like the first two here is actually 1 and the -1 for the roots. And then for this, we can combine them together. So these two becomes like 2 cos 4 theta for the coefficient of the z, and so on. 2 cos pi over 2, and then the 2 cos 3 pi over 4 then. And then after that, we can evaluate those like cos pi over 4, cos pi over 2, and also all like the 2 cos 3 pi over 4 then. Okay, so with that, we're actually able to like factorize this. So what they want 2 linear factors and 3 quadratic factors. Okay, so we can actually get these factors here, right? Next, okay. So this question is a bit long here. Okay, let's see. So write down in any form, okay, all the complex roots of this equation, okay, which is like W power 12 is equals to 1. Okay, so very easy lah. Okay, this one we can write like this is like a 2p pi over 12, okay, for the angle here. So we can simplify to become like p pi over 6. Okay, so the p pi over 6 here is we have got the p, okay? So again, our p we can write like from 0 to 11. Okay, we can write from 0 to 11 then. But what happened here is that I'm trying to use like the negative value of the p as well. Okay, so from the values which is like from 7 onward, right? I actually move all the values to become like a negative values. Okay, so this is why we actually get like all these the p, which is going from 0 plus minus 1 all the way until the 5, and then we have got like a 6 then. Okay, so the 7, 8, 9, 10, 11 has become the negative 1, 2, 3, 4, 5, right? So from there, okay, what is the second part here? The second part here is actually like, okay, explain why this equation z plus 2 power 12 is equals to z power 12 has exactly 10 non-real roots, and they may be expressed in this form. Okay, so it's quite a bit of the thing that we need to do here. So from there, right, okay, the equation which is like z plus 2 power 12 equals to z power 12, we can actually move the z power 12 to the bottom there. So basically, when we actually let this number inside, like the to be the w here, right, okay, we're actually able to express the z in terms of the w. So what do we actually wanted to solve here is that if you actually let this the w here, right, we are actually solving for w power 12 is equals to 1, which is why we have actually sort of like solve it in the earlier part. Okay, and we know that, okay, now when we want to solve for the z here, right, the z value is actually depending on the value of the w. Okay, so okay, when we look at the explanation there, so the equation star, okay, which is the z plus 2 power 12 equals to z power 12 is a polynomial equation which has a degree 11. So supposedly we should have like 11 roots there. Okay, and also that we have the w here, okay, is not equals to a 1. Okay, and like when z is equals to negative, when w is equals to -1, the z equals to -1 is also a real root here. Okay, so we see when z is -1, right, we can actually see from here straight away, it is actually a root. Okay, so the z equals to -1, okay, when the w is equals to -1 is already a real root. So here we see degree 11, supposedly we will have like 11 roots, and we want to prove that there's actually like 10 non-real roots here. So from there, we already identify one of the real root is in fact like the z is equals to -1. So from the 11, so 1 is gone. So the remaining 10 roots here, okay, are actually non-real. Okay, because we have already also said that, okay, like the z is depending on the w, right? And the w is actually all the values that we actually have from here. So the only values that it gives us like the real root is like the 0 and 6. So the others will actually gives us all the complex roots. Okay, so that is the explanation that we need to actually mention from them. Okay, so next. Okay, sorry, we look at the question there first. And we also need to like explain, okay, or show they can be expressed in this form. Okay, so we are starting with the, okay, z is 2 over w minus 1. We want to find an expression for the z. So for the w, we already have the expression earlier. We already solved it. Okay, so the easiest way that we actually get to the result, okay, is to multiply the numerator and the denominator here by e to the power of negative k pi over 12. Okay, we can actually do that. What happened, okay, after that is, okay, in the denominator, it gives us something very nice already. Okay, so in the denominator here is our favorite, like 2i sine theta there. Okay. And for the numerator, we can actually open up a little bit for the e power negative k power 12i there. Okay. So with that, we just have to tidy the things up. Okay. So like split the terms and then we divide by like the I, all sorts of thing there. So until we actually get like a nice result like this here. Okay. So that's for part 2. For the part 3, show that, okay, we have got this result. Okay. So it's not difficult for us to prove that. Basically, we just have to expand. So when we expand, we will end up like with like an I squared, which is a negative 1. So we have got a positive. Negative 1 squared is 1. So this is a cosecant squared. Okay. And then for the last one, okay, given that, okay, the product of the roots, okay, is negative 512/3, find the value of this, okay, sine square 1 or 12 pi, and so on. So how do we actually get that is, okay, so we are considering the product of the roots. Okay, so what happened in the case for the product of the roots here is that, okay, negative 1 is one of the roots. Okay, and for the other roots, right? Okay, the other roots, right, is having the value of like what? Is having the value of like the p here is like all the plus minus this 5 here. And this 5 here. So when the t takes the value of these 5, right, for the equation there, right? We have also like proven that, okay, in the part 3 here, it gives us this result here. Okay, so you can see the result here is like, because here the k, right, is actually like the k that we actually have here. It's actually our p here. So for plus and minus 1, right, when we actually like, because this is a root, this is a root. So this is, let's say when the p is equals to 1, let's say this is when p is equals to negative 1 there, right? So it actually gives us a cosecant of the negative half of like the 1 pi. Okay, so we have got like the 1 pi. So this is actually coming from the value where p is negative 1 and 1. This one is coming from p equals to negative 2 and 2 and so on. P equals to negative 3 and 3, negative 4 and 4, negative 5 and 5. Because we already multiplied the roots together. Okay, we multiply the roots together like this. We are getting all the cosecants. Okay, so from then, okay, we can actually just tidy up a little bit, just flip it and cancel out the negative there. So we actually have got this result. Okay, or the sine square, 1 over 12 pi, and so on. For this, it will be a 3 over 512. Okay, so the thing, okay, that we are looking at for the next question here. Okay, so use the De Mor's theorem to show that the sine 8 theta can be expressed in this form. So basically, I'm not doing much about it. So it's the usual stuff that we have been doing. So use the De Mor's theorem, start expanding, and then they just they want the imaginary part, which is they want the sine 8 theta. Right? So we take the sine 8 theta from the imaginary term there. So this is what you see here, yeah. Okay, and then we just change everything to the sine. Okay, we factorize out the cos and the sine first. Everything else inside there, we just change into the sine. Okay, or the cos. Okay, here change that into something in terms of the sine way. Okay, so with that, then we will have like the result like this here. Okay. So then, okay, what we have for the next part here is, okay, we are trying to do the sum. Okay, so it's actually like a different part of the question here. So use the De Mor's theorem to show that, okay, we have got sum of these. Sine of the n theta over 2 power n is like n equals to 1 to the capital N. Is given by this expression here. Okay. So, okay, first what I'm trying to do here is I'm letting the set here to be e power I theta. So now we're actually trying to sum this, okay, set over 2 power n then. Okay, because we want to get something like sine n theta. So we need to actually form the sum ourselves. Okay, so if you actually like start to consider this one here, right, the z power n is actually cos n theta plus I sine n theta. Bottom there, we have got like the 2 power n there. Okay, so with that, right, we can actually split, okay, we can actually split the terms there into imaginary and also the real part, both parts there. So we know that, okay, we're actually getting this one. So we want to have this. Okay, so we considered the complex number here already. And also another one that we're considering here is, okay, because the sign, this sign thingy, right, is actually obtained from here. So this is actually a sum of the GP, which is Z over 2, our N. So you now we really use the formula, okay, for the sum of the GP here. Okay, so we can tidy up a little bit here. Okay, until we don't get anything which is fractions. Okay, so you can see the line which is at a tick mark there. So after that, what we do is we are going to consider using the conjugate. So in the numerator, of course, we can actually multiply, okay, the e power I theta, everything there. For this set here, we replace with the e power I theta, and then later on we multiply with the conjugate of it. So 2 minus e power I theta, the conjugate is 2 minus e power negative I theta. Okay, so remember the conjugate that we're looking at here, right? It's not the plus, yeah. It's not like plus, and then this is like an I theta, yeah. Not like that, yeah. The conjugate should be we change the sign of the theta there, so it becomes like a negative theta. So after that, it's also solve the expansion. Okay, for the numerator, especially you need to expand it very carefully. Okay, so once you actually expand it very carefully here, so all these things, okay, the e power I theta thingy, everything you have to open up. Okay, when you actually open up, you actually get the numerator here. And for the denominator, it's like when we multiply the 2 minus e power I theta with the conjugate of it, it will actually somehow gives us, okay, the term that looks like this. So e power I theta plus e power negative I theta. So from that, it's actually, we know that there's a 2 cos theta. Okay, this is a 2 cos theta here. So that's, we're actually getting like a 4 cos theta in this case. Okay. So after that, okay, we actually wanted to find like the sum of this one, right? The sign here, right? So we just have to take the imaginary part. So just copy whatever that we have actually done from the imaginary part, and we're actually done with this. Okay. So this is a series, yeah. Okay. So next question. Okay. So right now in any form, okay, all the roots of this equation, okay, nothing much. Z power 5 is minus 1 equals to 0. So this is a fifth root of the unity. Okay, nothing much for this one. Okay, and then hence, okay, so they say hence find the all the roots of this equation. So why suddenly we have got this thing? So there are a few things that we could observe here, like, okay, they are actually going from a z power 5 to the z power 4 means that something that could be already factorized out, okay? And also now the variable, which is like the z, right, become the w minus 1. So we know what to do from there already. So we need to actually like let the z to be like the w minus 1, okay? So let's look at the factorization part first. So for the factorization part, right, is, okay, from the fifth root of the unity here, we know that z equals to 1 is a root, which is very obvious. Okay, so z minus 1 is a factor here that we can actually factorize this z minus 1 out. Okay, and what we actually have, okay, for the remaining here would be a polynomial which is having power 4. Okay, so this is our polynomial. So, okay, then what happens is that, okay, just now what we did was we actually wanted to like have like the w minus 1, right? So this set is replaced by the w minus 1 here. So the we let the w to be z plus 1. Okay, so with that, we're actually getting this equation already. And also they want us to solve, right? Okay, solve the roots of the equation here. So when we have got like the roots of the equation, there is like the w is depending on the z and is a plus 1. So we just take all the z from just now. This is our z and then plus 1 to add. And then remember the p here, we already factorized the z minus 1 out. So the p will not take the value of the 0 again. So the p value that we have here is 1, 2, 3, 4. Okay. So in this case, okay, once we actually write it in this form already, it's very clear that like, okay, the roots here, okay, would be real. Okay, so no need to say much. Once we actually have like this form already, it's already that, we know that it's not going to be real already. Okay. So, okay, and then what we have from there is like, okay, find the arguments of the two roots, okay, which have the smaller modulus. Okay. What we are actually considering here is that these four roots, okay, So what do they want? They want to find the arguments of the two roots we have the smaller modulus. We could, okay, here we could list down all the four roots here. Okay, let's say like W1, W2, W3, and the W4, right? We can list down the four roots here and find out which two having the smaller modulus. And the two roots there, right? We find the argument of them. We can do the manual step. So another way that we can look at it is we can actually look at the idea where, so W here, right, that we see here, right, is actually 1 plus e power 2p pi over 5. The p is 1, 2, 3, 4. So it means that originally, right, the e power like this thing here, right, is actually in a circle, okay, that has all the roots, which is like this. Okay, so if you have got like 1 to plus with that, right, means we're actually moving the whole thing to the right by 1 unit. Okay, so all these here would be our W's. You can see the diagram that I actually draw here is our W. Okay, so from the sketch here, right, we will find out that, okay, W2 and the W3 are the two roots which are having smaller modulus. Smaller modulus means the distance from the origin is smaller. Okay, so we identify already W and the W2 and the W3 here are having smaller modulus. Okay, they are having smaller modulus here. So then, okay, we will have to find their argument. Okay, we need to find the argument from there. So if you want to find the argument from there, so how do we actually find is, okay, remember for this is like, if the W0 is actually there, right? This is the root of the unity. So they will actually like nicely divide all the angles into like equal, okay, equally. So this one is 2 pi over 5, 2 pi over 5. So this one is for sure like pi over 5. Okay, they are actually divided into like equal angles like this here. So to find the modulus, okay, the modulus of the W2, right, is, sorry, the argument, okay, we want to find an argument. The argument of the W2 is here. Okay, so we can use the isosceles triangle to actually do it here. Okay, so we can use the isosceles triangle and we can find the argument of the W2 here should be a 2 pi over 5. Okay, so whereas the argument for the W3 here is just like the conjugate of that. So the argument that we actually have here is a negative 2 pi over 5. Okay. So yeah, the question that I've chosen is not that straightforward. So you'll find it like very challenging one. Okay. So the next question here, it's quite similar to what we did in the notes there. Okay. So what happened in the first one here is that, okay, they already say by considering this. Okay, the set is I theta. So sub in the I theta inside there, and we actually write out, okay, the polar form. Okay, so from the exponential form, we write it as a polar form. So we know we are going to find out the real part. Okay, so we want the real part there. So after that, okay, we can actually consider like, okay, we sub in the set also. Okay, the set. So this one we know that it's actually a GP. This GP is having like the first term is a set, the ratio is a set squared. And the number of terms there is an n, the capital N. So you just put them into the sum, the formula for the sum of the GP. So from the sum of the GP here, okay, the fastest way that we can get to the n is we multiply by the z power -1. Okay, so a lot of things get cancelled off nicely here. So you can see like the denominator is the z minus z power -1. So z minus z power -1 here is actually like a 2i sine theta. Okay, and then for the numerator, we just open up, okay, the z power 2n, which is cos 2n theta plus I sine 2n theta minus 1. So after that, we just have to tidy up. Okay, so we split that into like the real part and also the imaginary part by multiplying the negative I from there to actually get rid of the I at the bottom. Okay, so when we actually tidy the things up, we have the real and the imaginary. So they want the real part there, right? So we just say something like, okay, comparing the real parts, or we say we consider the real parts. This is the sum. And then in the second part, right, what happens is that, okay, suddenly we have got like the expression which is like, okay, the cos suddenly becomes a sine, and then we have got like the 2n plus 1 in front then. So what happened actually for this one is that we can differentiate it, okay? So when we differentiate the expression there, right? So when we differentiate the expression at the left there, right? Okay, we get negative 2n minus 1 sine 2n minus 1 theta. Okay, this is when we differentiate the left-hand side there. And for the right-hand side, okay, we need to use a bit of like the product rule to do that. Okay, we need to use a bit of the product rule to do that. So basically, we are differentiating like half sine 2n theta and then cosecant theta. Okay, it will be slightly complicated, but it's actually not too bad after all. Okay, what happened is because like from what we actually have so far, right, we haven't like really sub in the theta because you can see in the question there, the theta is actually like pi over capital N. So we can sub the theta inside there. Okay, in all the theta that we see there. So it's very good that okay, when we sub in the the pi over N, right, for all these theta here, okay, the second term that we're actually getting from here is giving us a 0 because we have got like a sine 2 pi. So it will become a 0. So, and then also like we've got the cos 2 pi is actually like a 1. So basically we just move the negative over there, then we can actually get the right hand side is just giving us this expression here. Okay. Okay, next. The first part of the question is we have the exact same question, yeah, in the note, so I won't actually go through that with you. Let's just focus on the rest of it. Okay, the second part here, okay, hence or otherwise show that we have got this kind of the result here. Okay, so we just need to see what actually happened from the first result to the second result here. So basically what we could see is that, okay, we see what are the things that has changed. So if you compare the cos term, right, it will become like the theta here is actually 1 over 3 pi. Okay, so it suggests that we can just sub in the theta, which is a 1 over 3 pi inside, okay, the expression. So we sub in. Okay, sorry, wait. Okay, so when we sub in the 1 over 3 pi into the theta there, the left-hand side here, okay, we have got the secant power k of the pi over 3. So this is actually 1 over cos pi over 3 power k. So cos pi over 3 is a half. So 1 over half power k is a 2 power k. And then the rest of it, okay, the rest of it, right, is all about like when we actually evaluate them. Okay, cot of the pi over 3, we can evaluate it, okay, which is like a 1 over 3. And this is like secant power n of the pi over 3, which is like a half, okay, power n, 1 over. So we actually got like this thing here. So we can simplify and do this. Okay. So similar thing that we could do to the last part then. So suddenly we have got this thing here. Okay, so again, we see what is actually like a change from the first line, okay, to the third equation, the third relationship here. So we can see here, it feels like, okay, it feels like the theta here, right, has become like an arc cos of the x. Okay, so that is actually what happened from there. So if we let the x will be the cos theta, means like the theta is an arc cos of the x here, right? Okay, we try to find out the other ratios as well, such as okay, we try to find the cot theta. Okay, so for the cot theta, it's actually cos over sine, where the sine also can be written as something which is in terms of the cos. So it gives us this expression here. Okay, so later on, okay, so later on, what happens is, okay, we just submit everything from there. This is the arc cos of the x. This is cos theta. So the cos theta itself is an x. So that's why we get the x power k there. Okay, and then the rest of it, like the cot is this whole thing, we have already just proven it. The theta here is the arc cos of the x. Cos power n is actually the x power n. So later on, just to tidy up. Okay, when we tidy up, so we are actually getting this result here that the question actually asks us to prove. Okay. So next. Okay. So let the omega to be this, okay, cos 1 over 5 pi plus I sine 1 over 5 pi. Show that the omega power 5 plus 1 is equal to 0 and deduce that we have got this relationship. So, okay, omega power 5 plus 1 is equal to 0 is really from like scratch, we sub in the omega and just evaluate everything, then we should be getting a 0, just like that. Okay. So, okay, and then after that is that, okay, we want to prove for the omega power 4 thingy. So now from the omega power 5, right, it becomes something that has omega power 4, means something that has been factorized. And then we know that, okay, like for like omega power 5 plus 1, right, one obvious root, okay, one obvious root is the omega is a -1. So in that case, we can actually factorize the omega plus 1, which is we actually getting this equation here. And when we say that, okay, when we say that the omega is not equal to -1, then we're actually having like this equation, okay? Because this whole thing, the bracket there is equal to 0. So we just move the 1 over there, then we will get this equation here, okay? And we want to find the rest of it like omega minus omega power 4, omega cubed minus omega squared. So omega minus the omega power 4 here, okay, is we are having something like this here. So what happens is we're actually changing in between the angles in different quadrants here. So here, cos of the 4 pi over 5 is actually a negative of the cos 1 over 5 pi. So we change back everything to the acute angle. Okay, so because like cos 4 pi over 5, right, it should be a negative value. And for the 4 pi over 5, right, is related to the basic angle of the 1 over 5 pi in the first quadrant. Okay, they have got some relationship like this here. So for this one, the sine 4 pi over 5, okay, is the same as the sine 1 pi over 5. Because again, 4 pi over 5 has the acute angle of the 1 over 5 pi. Okay, and the relationship between these two angles is that when we take the sine, they will actually have the same value because this is the sine of a second quadrant angle. So it will give us like the same value as the sine of the first quadrant as well. Okay, so we can see like the sine, the Einstein term get cancelled off. This is what we get. So we do the same thing for like the power 3 and the power 2 then. Okay, so for the power 3, that one, right, the cos 2 pi over 5 is written as a negative cos 3 pi over 5. Sine 2 pi over 5 is the same as the sine 3 pi over 5. Okay. So when we actually add up, we get like 2 cos 3 pi over 5. Okay. So what happened next, okay, is hence find the value of all this. Okay. So when we actually add up the cos 1 pi over 5 and cos 3 pi over 5, right? Okay, it's like, okay, we add something that is related to those. Okay. So for the left-hand side here, okay, we actually have something like this here. Okay, what is this? This is in fact the negative one. We have already like sort of like proven that. Okay. And we just have to rearrange. Okay, so we get like this is actually a half. Okay. So same thing we do to the multiplication. So in order for us to get like the cos 1 over 5 pi times the cos 3 over 5 pi, we multiply the results together. And for the left-hand side, this one here, right, when we expand, we will get something like, okay, omega power 7 and omega power 6 here. Okay, so omega power 7 is actually what? It's actually omega power 5 times omega squared, right? Omega power 5 is a negative one from the relationship that they give us here. So this gives us a negative of the omega square. So overall, it will give us a positive omega square. So for omega power 6 is the same thing. So omega power 5 times the omega, which is we get like a negative omega. So you get negative omega here. Okay. So when we actually like rearrange everything like this here, right, it will give us a negative one here as again. Okay. So you can actually rearrange it. Right. So after that, okay, we want to find that the quadratic equation which is having these roots and deduce the value of like the cos 1 over 5 pi. Okay. So the equation, okay, to form it here is like this is the x minus sum of root plus the product of root. Okay, so we already have the values there. The sum of root is half, product of root is a negative 1 over 4. So we can actually form an equation from there already. So the x that we have here, right, would have the root of like cos 1 over 5 pi and cos 3 over 5 pi. And from this like quadratic equation here, we are able to find out what is the value for that. Okay, the x value for that. So it means that one value like the like cos 1 over 5 pi and cos 3 over 5 pi here, right? One will take the positive root and then one will take the negative root. So in this case, because we want to find a value for the cos 1 of 5 pi, right? Because cos 1 of 5 pi is something positive, then for sure it will actually take the positive root there. Okay, so we need to actually mention something like this, like greater than 0, then only we can conclude the cos 1 of 5 pi is actually taking this positive root here. Okay. So okay, for this one, is actually like the binomial expansion. Okay, do we have enough time? Okay, I think yes, we have. So the set here, right? Okay, is we need to show that 1 plus z is given by this expression. So it's actually very easy to show that. So this is our 1 plus the z. Okay, and then the thing that we do later on is to use the double angle formula. Okay, so when we use the double angle formula, 1 plus cos gives us a 2 cos square half theta. Sin theta gives us a 2 sin half theta cos half theta. Okay, so the next step that we want to do here is to like factorize, okay, the 2 cos half theta there, so we can get the result from there already. So with that, okay, we are starting with like the 1 plus z power n. Okay, so we see here. So the 1 plus z power n here, right, is because we already have the result of the 1 plus z here, right? Basically, we just take the power n, and then for this one, the power n here, right, we use the De Mor's theorem. Okay, and at the same time, we can actually write this as like a binomial expansion. So 1 plus z binomial expansion is given by this form. Okay, and choose r with like the z power r because there's a power of the 1 there, right? It will still be always 1. Okay, so we'll just keep it as like the power, the z power r here. But the z here is cos theta plus I sin theta with a power r. So basically, we can actually split the terms from there at this here. So we want to actually look at like the imaginary parts. Okay, so for the imaginary parts here, when we actually like try to expand that, right? This is a result that we are getting. Okay, so that's why you see that okay, the terms here actually start with like the n choose 1. And then, okay, we just have to compare these with the imaginary part that we have from here. So it's this part multiplied by this part here. Okay, so we can actually get the result at the end here. Okay, so next, okay, this is a question that is a bit complicated here. Okay, but anyway, show that if the z is e power I theta, okay, and the z is not equal to -1, then we will actually have this result here. So basically, is to sum in the z is e power I theta, and we can quickly multiply by the z power -½ I theta. The reason is that both the numerator and the denominator will give us very nice result. The numerator is the usual 2i sine half theta. Denominator is a 2 cos half theta. Okay, remember these results here. It's super useful. So after that, it will give us just the I tangent half theta. Okay, and then after that, so hence otherwise show that if z is a cube root of the unity, then we have got this whole thing expression here is a 0. Okay, so let's see. So let's see, okay, we find out what is the set first for the cube roots of the unity, okay? And then, okay, what are we actually trying to do here is that we are trying to prove that, okay, so here's the thing. We know that, okay, the set power 3 minus 1 is a 0 because the set cube is a 1, right? So the first term here is definitely a 0 already. And then the next thing that we do here is that, okay, you see the set here, right, it could be like plus minus. Okay, it could be a plus minus 2 pi over 3 there. So for like the z square and the z here, right, we substitute, okay, that inside here. Okay, so, okay, this is the form, right, that we have actually proven earlier. Earlier on, we have already proved like z minus 1, z plus 1 is giving us like an I tangent half theta. And then the z here is having like e power I theta, right? So the theta here is like this, plus minus 4 pi over 3. So the result that it should give us here is like plus minus 2 pi over 3. Okay, this one also, it will give us an I tangent of the half theta. Okay, so from there, what we have is like, okay, tangent of the plus minus of the theta is plus minus of the tangent theta. Okay, the result is here, tangent theta. Tangent of the negative theta is a negative of the tangent theta. Okay. So for this one here, okay, for this one here is that, okay, here we are changing, okay, for this step, okay, I think I'll write for you this clearly first. So we are changing this to plus minus I tangent 2 pi over 3. But the 2 pi over 3 is what? Is negative of the tangent pi over 3. Okay, we change the 2 pi over 3 into the acute angles. We get negative of the tangent pi over 3. So the negative minus plus multiplied by the negative will become the minus plus already. So from here, the second last line that we see there, they will actually cancel off. So after that, okay, we will actually have like the 0 in this case here. Okay, so this is one of the way for us to actually simplify this. Okay, you could also look at the masking. There are like a lot of the alternatives that we could do here. Okay, so but for the last part here, hence write down the three roots of this equation and find the other three roots, give your answer in an exact form. Okay, so this is really like a lot of work to do. Okay, so first, okay, is to look at like, okay, so what happened in this case is that we realize that this, right, okay, is actually the numerator when we combine all this into a single fraction, okay, is the numerator of that, okay? So if it is a numerator of that, right, it means that the set, which is a cube root of the unity, all the roots are also like the roots of this equation here, okay? Because what happened here is that Z is a cube root of the unity and it satisfies this equation. And from the second line here, we are getting this equation here. It means that all the roots here are also the roots to this equation here. Okay, so what we do here is, okay, now we see, we expand everything, okay? And here, because like the set cube minus 1 is a factor, because what happened, like cube roots of the unity are roots of this. So it means that the set cube minus 1 must be a factor to this quadratic, this equation here. Okay, again, cube root of the unity is a root of this equation. Okay, so we can actually do the long division from there. It actually gives us quite a nice thing here. Okay, in which what happened here is that, okay, we can actually have like the factorization again. This one we can actually factorize further. We can take out the z plus 1 from there. Okay, this is a minus here. I'm sorry. Okay, so we can take out the z is equals to negative 1 again, right? And we will have just the quadratic. So the quadratic here, okay, is we just have to use the formula to actually solve for that. Okay, so at last, okay, what happened, okay, to this case here is that the two roots of this equation, this is actually our cube root of the unity. Okay, and the other three roots here is actually like listed here, this and these two. Okay, so that's how we actually look at this question here.